Good morning, everyone, and for those on the East Coast, maybe good afternoon. Um, my name is Anand Padmanabhan, and I'm a research associate professor in the Department of Geography and GI Science at the University of Illinois at Urbana-Champaign. And on iGuide, I play the role of the managing director. iGuide is the Institute for Geospatial Understanding through an integrated discovery environment, and we host this almost weekly basis, this what we call as virtual consulting office or a VCO. And this covers various topics, and you can sign up for iGuide email lists using the QR code in the bottom, or you can go to the website, which is i-guide.io, and sign up there. But we have this very regularly throughout the year. And today we will have a talk from Alex Michels. Alex is an assistant professor in the University of Texas at Dallas. Before that, he was at Urbana-Champaign, and he got his PhD from here. And Alex is an expert in various topics, including cyber infrastructure, GIS, and now he's going to be talking to us about computer vision and how to use street view imagery, specifically in his role as the UCGIS community champion. So UCGIS is a partner organization of IGAD, which is the University Consortium of Geographic Information Sciences, and they host this annual event called the Community Champion, which we have five community champions this year. We will have talks from all of them. You can see some of them actually upcoming. Alex is the first one to be scheduled for that talk. And you can see the upcoming schedules of all our VCOs on the right side. So that's our VCO series and iGuide, and you can always reach out to us at help@iguide.io. So without further ado, I will pass on the Zoom floor to Alex, and Alex, you can take it away.
Sounds good. All right, can you see my screen?
Yes.
Okay. Okay. So yeah, today we're going to be talking about exploring street view imagery with computer vision. And we're going to start with a few slides just to motivate the topic, but then we're going to head to the iGuide platform for more of a hands-on walkthrough of the materials. These materials are designed to work with limited technical background. A lot of the classes that I teach have very interdisciplinary attendance, so we get like GIS, but we also get criminology and other social sciences. Um, but there's still more work to do. So if you have a dumb question, feel free to ask, because if it's something you're wondering, it's probably something that a student's going to wonder. And then just generally feel free to ask questions throughout if something's unclear or you're just not understanding. All right. So first, breaking down the title, what is street view imagery? It's just an image taken from the level of a pedestrian or a vehicle on the street as opposed to aerial imagery. So in GIS, it's very common for us to work with like satellite imagery, remote sensing data, but it has some limitations compared to street view imagery. I'm actually would be curious, the test to run on some students would be like, if I show you just a top-down image, can you identify, like, is this our university or not? Because this isn't how we see the world. This is. And it's generally really available now. So coverage varies spatially, obviously. For example, in the US, we have pretty good, Northern Canada not. And in 2018, it was estimated to cover over half the world's population. And I'm sure that number's only grown. But for Google, they have pretty good coverage, but alternatives to Google do exist. So for example, this is Mapillary, which is an open provider of Google Street View imagery. You can see their coverage in the US, but then I just zoomed into, this is UTD. You can see even with these relatively minor residential streets, there's pretty good coverage. So how might we use this? It's often more useful than aerial imagery because it generally provides higher quality imagery and it better reflects human experiences in those places. So for example, when I say higher quality, what I really mean is really fine-grained remote sensing imagery. You might get down to a couple meters, maybe even centimeters, but it's not going to beat someone's iPhone 10 feet away taking the photo. So just a couple of examples, detecting really small objects like lampposts, Might be hard depending on the resolution of your satellite imagery, a signage on buildings that are designed for street view. So for example, when you put the hours of operation on the front of the business, that's for someone on the street to see, and the satellite just doesn't have the correct angle to get that. Another hot topic recently has been green space versus perceived green space. So asking questions like, does a rooftop garden provide benefits to someone on the streets? If I'm just walking by, I don't even see the rooftop garden. I might get some benefit from like air quality, but I'm obviously not getting the mental benefit of seeing the green space. So there's a pretty wide variety of questions we can ask with this type of work. And just to provide one use case in more detail, so this is some work from Xinlin Ma et al. 2025, where they were using Street View imagery to analyze urban changes that are difficult to examine using remote sensing imagery. So they have this 5R framework where you can talk about the different ways in which urban retrofitting happens. So the most common one that we think of is just like rebuilding. Like we tear down the building, put up a new one. But that's not the only way that urban change happens. There's recapital, so investing in areas. Again, we might see that from remote sensing. Re-inhabitation, so just the people who live there were using that building no longer do. That might be hard to detect. Rebuilding is pretty easy. Retransportation may or may not, depending on the resolution. Recapital. So it could just be that they changed the function of the building. Regreening, again, depending on the resolution. We could use things like NDVI, but we still have those perceptual questions. So hopefully this helps to motivate a little bit of like, why should we care? But of course, we generally don't have the budget or the manpower to process all of the street view imagery. So we have to rely on computers. In the field of computer vision, will help us analyze it all. So CV is the branch of artificial intelligence that applies AI and machine learning techniques to imagery specifically. So hopefully that provides just a 1,000-foot view of what we're going to be doing, but I wanted most of this to be more of a hands-on walkthrough. So the 3 notebooks that we're going to walk through today, the first is images and computer vision. So this is really basic fundamentals of how a computer sees pictures and a really naive approach to computer vision, just to help motivate, especially the non-technical background. We have a lot of students who don't really understand like how a computer even stores images, so that helps walk through that. And then object detection with faster RCNN. So here we're going to use a pre-trained traditional computer vision approach like a CNN to do a little bit of detection. And then our third notebook, we'll be using vision language models for street view imagery. So we're going to walk through just a small pre-trained VLM. This notebook does take a while to run on iGuide platform for now. We're working to get GPU access for that, so it should be faster in the future. So I'm just going to demo it on my local computer, but hopefully we'll get it sped up over the summer and available soon. So if you haven't used the iGuide platform before, it's platform.i-guide.io. Copy that to the chat. And when you get to the web page, you just want to click this sign in at the top right. Even if you don't have an account, that's fine. It'll redirect you to something called CI Logon. There, you're going to pick your institutional credentials. So, for example, University of Illinois, University of Texas at Dallas, and just sign in using those credentials. And then if you have signed in before, we'll just sign you in. If you haven't signed in before, it might ask a couple of questions about just registration. But overall, it's a pretty painless process. So I'll give everyone just a minute to, again, head over to iGuide platform and sign in / create an account. Of course, if there are any questions, feel free to ask as we work through this. All right, everyone made it over to iGuide platform and signed in. So once we're there, what we're going to do is search Intro to Computer Vision or some variation. You should find the notebook, but also just post the link to that notebook here. So you should see something like this when you get there. And the nice thing about iGuide platform is that we can host notebooks so we can look at them. We can also execute them. So we can click this run this notebook button. And what this does is it brings us over to the iGuide Jupyter, and it also pulls all of the code data that you need from GitHub and opens it up for you. So you should end up with something like this. Again, feel free to ask any questions or issues that come up. Hopefully this will be more of a hands-on than just a normal lecture. All right, sounds like we haven't had any issues so far. So this first notebook, again, is just how does a computer see an image and the very basic concepts behind computer vision. So imagery is one of the most ubiquitous types of data, and it's underutilized because it's time-consuming to analyze. And here we're going to talk about how a computer sees an image and provide a general introduction. So if you haven't used Jupyter before, you can click on the cell and click play to run that cell. And you see that star, that just means it's running, and then the one means it's done. You can also use Shift Enter. There's a few other options. But for those who don't come from like a computer science background, the way a typical computer stores imagery is RGB, red, green, blue, and then all the other colors are just combinations of those three values. So a lot of times a computer will store R, G, and B between 0 and 255, it's the integers, and then we can get all these different combinations just from that. This differs from like a printer where you have CMYK, cyan, magenta, yellow, and then K being black. So there's a couple different ways of doing this. So just to show you what this looks like, I can just take three random colors, red, green, blue, and I can run that, and we can get our purplish color. And then the next cell, feel free to play around with these values. So let's make it significantly less green. We end up with essentially red because it's almost entirely red. Do that, end up very green. You can even mix them to get this. I'm not sure what this color would be, chartreuse. But yeah, this is how a computer actually stores this data. So functionally, what an image is to a computer, it's just a big grid of numbers, three numbers, red, green, and blue. And of course, we can always just generate random data and plot that. So like this is the static that you'll see on like old televisions. It's just that random noise. And we can also break it down into those three bands. So we can look at the red, the green, and the blue all separately, or combine it together to get that random noise. So any questions so far on like how a computer stores these images and kind of how we get the picture that we're looking at? All right, so now let's work with real imagery. So this data comes from Kaggle. So it's right here if you want to check it out and download all the data for yourself. I only saved a few samples from this because it was quite a large data set. And then we're also going to be pulling some data from Mapillary, but these examples come from Kaggle. So we can use this load image and just give it the path file to load it and plot it real quick. So this is street view imagery from Google showing a road going through what looks like a mountain pass or hilly terrain. And again, we can split it up into those three bands, that red, green, and blue. We can plot each separately just to see how it all comes together. So now that we kind of understand what an image looks like to a computer, how do we actually analyze the imagery? Because just having the red, green, and blue is very helpful. So one really naive approach would be if we look at each pixel individually, so each grid in that cell. And let's say we want to understand how much green is in this image. Maybe we're looking for green space. We could set up a really simple process where we say, okay, if there's any green and there's not too much of the other stuff, we're going to say that cell is green. And then we can just go through every single cell in our grid, every single pixel in our image to decide what's green or not. And if we run our image through that, it works okay. Like we got the trees, some of the grass, the hill, It's fine. Um, and feel free to play around with this. Maybe you can get it to work even better. Maybe you can find some other simple heuristic. But generally, this approach doesn't work very well. So if we pull up another image from our Kaggle samples, hopefully it's immediately clear why this approach won't work that well. Like this is green, technically, yes, but if we're interested in green space, that's not quite what we're looking for. So when we run this same process through, we identify the sides of these buses as green. And while it is technically green, it might not be what we're looking for, green space. So hopefully this helps to motivate why we need slightly more complicated processes to actually do this computer vision and not just rely on these simple heuristics. So did that notebook work for everybody? Any questions or feedback at this stage? All right, hearing none. Oh, go ahead on.
Yeah, it worked. Thank you. Thanks.
So yeah, next we'll head to this. So if you just have this folder browser, you can open the second notebook. It's also on the iGuide platform. If you scroll to the bottom, you can see these related elements, and both are linked here. We're going to use this object detection one first. But since they're all in the same GitHub repository, they all just got pulled together with that first click. The clear outputs. All right, so how do we do more actual computer vision? So the last notebook was looking at a really basic heuristic, so it wasn't really computer vision AI that we think of. So here we're going to use a pre-trained model to see how more traditional computer vision works. So when we talk about computer vision, there's a lot of different tasks we can try to perform. One is classification. So we have an image and we just want to know what category does this image fall into? Is this a picture of a cat or a dog? So that might be here. So we have this picture, we say this picture is a cat. We can also do classification with localization. So I want to know what's in the image, but then also where in the image is it. That's what this is doing. It's saying it's a cat, and this is where in the image the cat is. We could also related task is object detection. So we have maybe not just one thing in the image that we can classify the whole image, but we want to identify different objects in that image. So here we have a dog, and a cat. You could also do segmentation. So segmentation is more related to that last notebook where we're doing a pixel by pixel. I want to know, is this in a part of some object? And if so, what object is it? So here we're showing this, all of these pixels are one dog, all these pixels are another dog, this pixel's a cat. So semantic segmentation is over here. This is just, I want to know what categories things run into. So grass, cat, trees, sky, or instance where I want to be able to differentiate different instances of dogs. So this is just to give kind of an overview of the different things we can do with these types of models. But specifically, we're going to be using a pre-trained model for object detection. And we're going to be using something called convolutional neural networks. So the math is complicated. We're not going to walk through it, but there's some great visualizers here. So this first one will show you if you draw a number here, it'll show you how all the different layers in the neural network work together to identify that it's a 5. And obviously, walking through all of this by hand is a lot, but hopefully this helps you visualize that it's not just like magic. It's just identifying different features. It's looking for these curves. It's looking for the top there. Another great visualizer is here. And this one shows different, hopefully this one loads. Try that again. There we go. So it shows with different images. So for example, this teacup, there's the red, the green, and the blue channels. And it shows how that flows through, and you can actually see all of the different math if you really want to walk through it slowly to determine all of the different layers in the neural network and then how that maps into different potential outputs. So for example, espresso has a very high value here, but there's even some potential that it's still an orange. It's not entirely sure, or maybe even a bell pepper. So again, the math here is pretty complicated, but really all you need to know is we're mimicking a brain with these neurons that are really just values and these connections between them. And through a bunch of math and optimization, we can get these connections to work so that we get the answers we want. But even then, it's not going to be perfect. Sometimes it thinks the car might be an espresso. And specifically, we're going to be working with a pre-trained model so that we don't have to do all the training and all the math. And we'll see how that works. So first, we're going to import all of our packages. And then this is just a quick helper function to just show a list of images. So let's load that Kaggle. So this is 0.png. So this is the same image that we were working with in our last notebook, but we're just going to load it as the actual values. So again, this is the red, the green, and the blue. And then we run it through our little decoder just so that the computer read it properly, and then we can just plot it. So here's the three images we're going to be working with. It's image 218 and 255 from that folder. So we have one that's just a couple buses, one that appears to be like a dash cam of a car coming forward, and then one that's image of, it appears to be a home. So the way we're going to use these pre-trained models, you can actually go to PyTorch and look at all the different models and weights that are available if you want to, but we're just going to be using this faster RCNN ResNet 50. We're going to use the default weights. So to do that, again, you can check out all the documentation on what weights are available for different tasks. And then you just can load them here. Now, most traditional computer vision models can only see the objects that they're trained on. So this means, similar to our examples up here, where we had a set number of outputs like espresso and sports car, taking a while to load. It only knows what it's seen before. So this means you have to be mindful when you're selecting these pre-trained models, ensuring that the models can be have been trained on categories you're interested in. So our weights object, again, from PyTorch that we're just pulling, has a list of categories that it's been trained for, and we can look at that in the metadata. So if we look at the length of the categories in the metadata, we can see that there's 91 different categories, and if we just print that list, we can see it's a relatively extensive list. There's some interesting inclusions in here. For example, kite and some random food items, potted plants, cell phones, etc. But even for Street View imagery, we also have a lot of useful things like people, bicycles, cars, buses, etc. But again, if it doesn't fall in this list, it can't see it. It's only been trained for this list. So here, what we're going to do is take that model, and we're just going to give it those default weights we have. And then we're going to run this eval. All right, so that's just updating it with all the weights. And we can take the images that we gave it in our image list, run that transformation just to make sure that all the numbers are the way the model wants it, and look at our outputs. So this is just running these three images from above through our pre-trained model. And again, feel free to butt in with questions. I have the chat open if there's any questions or concerns at all along the way. But yeah, we got our outputs. So the way the output looks is we get boxes. So these are those bounding boxes like this that show us where in the image the thing might be. Then we also have labels. So these are the values in our list of categories that it thinks it is. That helps us determine what it thinks it sees. And these are our scores. So this is how certain it is that that object is there. And we have that for each of our different images that we walk through. So here we see we have three things in our outputs, which makes sense because we gave three images, and each output has the boxes, so the bounding boxes, the labels of what's in the box, and the scores. And here, what we're going to do is just, if the score is at least 80%, 0.8, we're going to show the image with that bounding box. So here we see in the first image a bunch of people and both buses. Here it found the car, and here it finds this bicycle behind the tree. All right. But again, it's not showing you everything in the image. There's obviously other things. There's all these little bushes, there's this road, there's a power line, but it's not in the list, so it's not going to show up. And the labels are a bit hard to see from the image. You can also just print the labels if you really want. So that's for the first image, for the second image, for the third image. So this is just wrapping all of that up into one function where we put the image through the model, we get the first output, and then we draw the bounding boxes, just so that we have that for when we do our own stuff. So now let's talk a little bit more about street view imagery. So we already looked at this image, and there's a great UCGIS body of knowledge article about this as well, if you're interested. I also recommend this paper by Dr. Bill Jecky. This is a great review on street view imagery. But we're going to be analyzing data from someone called Mapillary, because Google has some pretty restricted terms of service. Generally, it's still pretty common to use it for research purposes, but sharing the data might get you in trouble. So we're going to use Mapillary because it has CC BY SA. So you just have to attribute where you got the data from. And you can check out some of the data sets here. How these scores are generated. I'm guessing it works as a validation, but I was curious. So the scores are, it's obviously pre-trained models, but what that's saying is how certain are we that the thing in the image is actually there. So going back to, let's back up. Let's take a second to load. So again, the computer doesn't actually know anything. It's just a bunch of math that generates probabilities. So here with this cup, we see that even though it most likely is an espresso, there's also some small score that it could be a bell pepper or an orange. So that's just filtering to say, okay, I only want the things that we're confident are in the image. That's essentially what that score value is. So here, we're pretty certain this one's pizza, so there's not really anything weird. Ladybug. Okay, so the sports car, but there's a small chance that it's an espresso still. So the scoring is just to make sure that we're only looking at things that we're confident are in the image. And if you want to, in this, you can, so where we have a score threshold. You can lower it way down if you want to whatever value and rerun. And you'll see you have a bunch more labels. So for example, it thinks this little piece of a tire might be a person. And it thinks, I can't even tell what's going on there when we output the labels. It thinks there might be a bench here, which there might be. So yeah, there's a little bit of an art and science to exactly where you set that threshold, but that's all it's doing. It's just the certainty of the object, essentially. But yeah, getting back to Mapillary. So if you go to mapillary.com, you can view the images. You can view their map. And then if you click this ... there's a download button. So let me put this up real quick. So I believe this takes us to an image at UT Dallas. Yeah, but you can pick an image anywhere. This ... download the image. And then we can load that image. So here, what you're going to do is download the image and then upload it here. So you're going to click this upload button, and that'll allow you to select it. And then you just change this file path to point to a different image. And then when you load it and run it through our object detect function that we defined, it hopefully will run the model through. Now remember, it only sees the things that it's been trained to see. So here it sees the stop sign, the car, and the car. So there's a chance that you run it and there's nothing in your image that it can see. But this is just one way to show you that you can actually do this yourself. All you have to do is go download an image and try it out. So I'll give everyone just a minute or two to play around with the mapillary. So again, the link is right here. And feel free to look around. You don't have to pick an image from UT Dallas. You're going to upload it by clicking this button after you download it. And then you just change this to where and here it is. So this is saying data/utd.jpg because it's in the data folder and it's called utd.jpg. And again, if there's any questions while we walk through that, feel free to raise them. All right. Do we have anyone actually working through it? Because I'm happy to wait, but if everyone's just staring at the screen, we can also move on. But yeah, if you're working through this or if you have any questions, feel free to raise them. See what the coverage is on Mapillary. So I can go to Champagne. It's not great, but there's still some imagery. All right. So I haven't heard anything, so I'm going to move to the next. Just take a. Okay, so you don't have to take a screenshot. What you do is zoom in, pick your image, and then you open the image up and do this dot dot dot, and there's a download image. And just remember that it's all CC by SA. So if you use this for your own stuff, if you share this data, you do have to say where you got it from. But other than that, it's a very permissive license, which is very nice compared to Google, which lawsuits. You don't want lawsuits. And then you just upload it with this upload button. And then you change this to the location in here or the name of the file. And then you just have to run this to load the image again and this to detect. And then our third notebook. So this one takes a while to run on iGuide platform. We are working to get it working with GPUs, so it'll be faster, but for the sake of everyone's sanity, I'm just going to run it locally. But again, it does work on the iGuide platform, it just takes a while. So this one is vision language models for Street View imagery. So we're going to use a vision language model, which is like a large language model, ChatGPT or Llama or Claude, but it can also see images. So specifically, we're going to be working with this model from Hugging Face Small VLM. And it's already a pre-trained small language model. So this will run on the iGuide platform or on your computer. So I'm just going to run it on my desktop. On the iGuide platform, it takes a little while, but it'll be sped up once we have the GPUs. And it's small because it does not use significant amount of RAM. It's pretty low. So it's reasonable to run without using, a supercomputer or all the GPUs in the world. So to run this, we're going to import a couple packages here. And then this line of code, if you have a GPU, you can use the GPU. If not, just use your CPU. So you can see I'm just using my CPU. I don't have anything fancy. And then here, we're going to get the model from Hugging Face. So just use this pre-trained. And we're going to use this image text to text pre-trained encoder. So this is just going to help us give it an image and some text, so a prompt, and then we're going to get text out. And then just load that same image we've been working with. And the way you get prompts, it looks like this. You got to give it the image, And then you're also going to give it a prompt. So your text. So here I'm just going to say in 20 words or less, describe this image. And then we're going to apply this chat template. Going to give it the prompt, and we're going to send it to device. So I think this is more necessary if you're using a GPU, but it's just there in case you need to send it to the GPU's memory. And then we can ask the model to generate and provide it with a token limit for its input. So since I said 20 words or less, I'm just going to set it to 500 max tokens. Tokens aren't necessarily words. You can kind of think of it as like syllables almost for the computer. It's not quite that. So I do recommend, especially if you're running this locally or on any platform, set it somewhat low. But let me just run that. So it's going to take probably 30 seconds to a minute. But yeah, tokens are like bite-sized chunks that helps the model understand the word better. So a word like unbelievable might be cut into un, meaning like the opposite, believe, the root word, and then able, like the suffix, just as an example. So that will generate, and then you can decode what it outputs and print. But again, that's all going to take a minute or so. So yeah, if there's any questions or concerns at this point, feel free to ask on this or the last notebook.
Hi, Dr. Michaels. While we wait, I do have one question, and you
Mhm.
might actually mention this later. But when I look at this, my one question is, so how do we validate that what it's seeing is actually correct? I mean, we have scores, and then if we're dealing with just one image right now, so we can actually see see whether or not they're actually validated or not. But later on, if we use with multiple street views and multiple image, it's going to be hard to kind of validate. And is there any way that we could kind of be sure that it's seeing what it should be seeing?
Yeah, it's a great question. So when we're using these pre-trained models, you can usually find the paper associated with it, and they generally have run the model against some benchmark data set with labels. So it'll tell you at least the accuracy or other performance metrics on that specific benchmark data set. But of course, there's always the risk that if you use a different data set, you're going to get different results. So it's never 100%, but I think as long as you're using models that are published, they have good benchmarks, and you do at least a little bit of a sanity check. You run it through a couple different things and verify manually that you're getting the results you're looking for. But at the end of the day, there's no guarantee. There's random numbers, unfortunately.
Okay, thank you.
So here we can see we did get our output, and it says it's a road with trees and mountains in the background. So it's for a description of 20 words or less, that's pretty decent. I mean, we can also go through and ask it other things. So this is just taking those last couple of chunks of code and putting it together into one function just for simplification. And then let's ask it how many trees are in this image, provide only an integer. So while that's running, this is obviously a bit of a trick question. How many trees are in this image? Anyone have a guess? How about you guess what you think the answer is, and then maybe you also guess what the model thinks it's going to say. No one brave enough to take a guess, or are we all zooming in trying to count all these ones in the back? At least four is a good answer. There is at least four. Unfortunately, I told the model provide only an integer, but we'll see. Maybe they will just say four. So yeah, this is obviously a trick question. If we're talking about the background, the answer is probably thousands. But just to show you kind of what Christine was mentioning, just because you have the model and it's the best tree trained model, whatever, you can't always rely on the answer. So here it says two. I'm guessing it's picking this one and this one, which is a reasonable answer given the image. But of course, if you're using this as one step in a pipeline and you don't do any validation along the way, this is going to skew your results, but it's still better than manually counting all these pixels in the background. So there is some trade-off in accuracy versus time. And if you give ChatGPT. I think the last time I gave ChatGPT this image, it just didn't give me an answer. But I'll have to try that again. It just kind of spun there for a while. And then, yeah, you've heard of the old adage, don't miss the forest through the trees, and the VLM missed all the trees in the forest. But of course, no reasonable person, and especially at this resolution, I don't think even an unreasonable person would be able to get a correct answer. So while this shows that the models aren't perfect, the models are still decent. It still gave us a reasonable answer. And this is an openly available small vision language model. So you can imagine the proprietary models, the more complex models, give you better ones. And then just like with the last notebook, where you can go get your own image and run it through with your own prompt, we could do that at the end here. So here we'll just load that UTD image again from Mapillary, and we're just going to say briefly describe this image. And then we just run this function. Would this model be feasible for use in generating alt text images on websites? Again, I think it depends on the accuracy versus cost trade-off. So if you don't have a lot of images and you want the descriptions to be highly accurate, I would just do it manually. But yeah, if you have like hundreds or thousands of images and you just want the descriptions to be good enough, it might be a good use case. Yeah. Ooh, we got a bunch of questions. Okay, so can Street View imagery analysis be used to measure walkability of the built environment specifically for people with disabilities? That is a great idea. Yeah, you could apply probably more traditional Street View, traditional computer vision images to look for example, like sidewalk cutouts, where, like, for example, wheelchairs are able to get up onto the sidewalk. You could look for building ramps. You could do a lot with that. Is Mapillary completely free to use for research purposes, or are there restrictions? So my understanding, I'm not a lawyer, is that all images are shared under the CC BY SA license, because that's what it says here. Again, that may come with caveats, but CC BY SA just means that you can use it, you just have to provide attribution. So it's pretty open. It's about as open as you can get reasonably. And then the third question was interested in measuring neighborhood environment change over time using Street View imagery. With Mapillary, how far back does the coverage go and what intervals? That's tougher. I'm definitely not an expert in Mapillary, and the coverage probably varies drastically on where you're going to have multiple temporal standpoints. For that purpose, you might be better off using Google. And Google, it's very common for people to use Google imagery for Street View analysis. Just know that you're a little bit in the legal gray area, and you probably can't share the data because I think technically by the terms of service, even just downloading the data is against terms of service. So you have to be a little careful, but there's no shortage of papers out there doing exactly, well, very similar topics to what you're talking about using Google Street View. So don't let that completely scare you off. Yeah. So yeah, we got a red stop sign is in front of a parking garage, and that is very true. I will give it that. So yeah, that's all I had for today. I'm happy to answer additional questions. And again, we're hoping to get this working on the iGuide platform more efficiently. So it technically does run. It just takes, it took a minute or so on my computer. It takes a little bit longer on the platform, but we're hoping to get GPU access, which will speed things up significantly. And of course, you can also just run this on your own computer, which is one of the reasons why I picked this small VLM. As long as you've got about 5 gigs of RAM, feel free to run it. GSV is fairly reasonable in terms of price. You could also buy imagery. That's also that's a great point. I'm kind of working from the no budget standpoint, and I know lots of people who just kind of go scrape their imagery, but you could also just pay for it. That's a very good point. And there are probably other commercial Street View providers as well. I think Cartaview is another open one. So there's a few different options there. As Mapillary doesn't have enough coverage for the neighborhood, is completely only So like I said, it's going to vary. It's going to vary a lot spatially. So this is all volunteer data. So if I go to my neighborhood here around UT Dallas, you can see even these little residential roads have pretty good coverage, but it depends a lot on where you are. And then all Street View sources shares the same time capture limitation. How can we handle this limitation of fair comparison? That's a great question. So they do all have that, but I believe Google is better at getting multiple images in the same location. They also usually take panorama. So I have seen a few papers. So for example, this work that I talked about looked at the same place in different snapshots in time. And they used Google Imagery because they were able to find more places that had multiple timestamps for the imagery. How are these three approaches sufficient for quantifying neighborhood features? Which one does outperform? So the first one I definitely wouldn't recommend. That's more a naive approach to kind of motivate why we're doing this computer vision. The second one is probably easier to do this validation because if you have labeled data, you can determine like, is there or isn't there a bus? Like it's kind of a binary question. So it's easier to score and do benchmarking. This third approach, though, is more open-ended. So you're able to kind of scale up faster, but validation is going to be harder. This small VLM and open weight model that we can fine tune, I believe so. Yeah, and there's a few different, yeah, there's a notebook on how to fine tune it, or there was. And then do we need human labeling to fine tune open weight models? What size do you suggest? That is definitely a bit outside of my area of expertise. I generally am more of a user of these models than an architect or someone who does fine tuning. So I hopefully will get better answers with the upcoming VCOs. I think Quisheng has a great one in a couple weeks where he's going to be talking about these open source GeoAI workflows. But yeah, happy to answer any questions. Was anyone able to run the second notebook with your own image from Mapillary? I know when I ran this in class, a lot of students were like surprised and happy that they were able to do it because they kind of just see this as magic. So when they actually were able to do it themselves, they're like, oh, okay, it's not magic.
And I guess people can feel free to unmute and
Mhm.
ask Alex question rather than just typing in the chat. So yeah, feel free to do that.
I just have a simple comment or question about running it because I couldn't run it. I did sign in using my university credential, but I think you might have to actually log in and create an account to actually run this. Is that how everybody did it, or is it just me?
If you made an account with University of Texas at Dallas credentials, you should automatically have access to the Jupyter. What step did you get stuck at?
The button where it says run this notebook is, and it's not able to on my screen.
Uh, Try refreshing the page and see if you're still signed in.
I did try refreshing twice and I was logged in. So I was going to try after today's lecture though.
No, that's good to know. That's a potential bug. I guess the next debugging step would be sign out and sign back in. But yeah, definitely we can work with you to try to get that resolved.
Yeah, I'm going to try again after this. Thank you.
Mhm.
Yeah, and if you have issues, you can send an email to help@i-guide.io. So our
There's a
development.
contact us
Yeah, so
as well.
there is a contact us as well. And
Yeah, that's all I had for the day. So if there's no other questions, and if no one else has concerns about being able to run it through the second notebook, we can wrap up, and I'll just stick around a few more minutes for any additional questions or concerns that may come up.
Yeah. Thank you so much, Alex. Yeah.
Mhm.
Any final questions before we wrap up?
Alex, I'm curious, have you done anything with vision language action models as well?
No, what is the action in vision language action?
I don't know much about it myself. I was just told about it earlier today. But apparently kind of a new generation where you can also have the logic of what to do with image or with the things that have been extracted from it. I don't know. I was hoping maybe you could enlighten me, but yeah.
No, I'll have to look into it. So one of the use cases that I'm interested in VLMs for is Asia-based modeling. So it sounds like that's exactly the kind of thing I need to look into, though. So thank you for bringing that up. Any other questions, concerns? Here to help. And also feel free to reach out. It's just alexander.michels@utdallas.edu if you have any concerns. I think it's also on my iGuide profile. Okay, yeah. So this is the ugly email, but it'll send to the same place. Yeah, so Rachel, I don't think the action is the blurring. I think that way predates vision language models. But that raising that is an interesting point. You will end up with some weird blurring in some Google imagery that could distort some of your results. BLM is still running. Yeah, it takes a while. A platform, but we'll hopefully get that sped up soon. Any other remaining people able to get this working with your own mapillary image?
Okay, if there are no other questions for Alex, we could formally wrap this up and we can stick around for another few minutes if people still have questions or want to talk to Alex one-on-one. Thank you all.